So I am here to talk about testing, which, as everybody knows, is the most boring topic, right? And I'm also the last speaker in the day. That's a very dangerous combination. So I'm going to do something a little bit experimental in the interest of keeping everybody awake. So the problem, as you've heard from a bunch of other speakers today, is that testing distributed systems is horrible. Like, it's really, really nasty. You've got a distributed system that means you've got code on multiple computers, and they're talking across an asynchronous network. And as Andrew mentioned, right, like those messages could get dropped. They could get arbitrarily reordered. These computers have different clocks. These clocks could drift out of sync. It's like bad stuff. Like, how do you test that? So maybe it would just be easier to give a talk about testing single node systems instead. But you know, the problem is actually any modern software, right? Like single node systems too. They're all horrible. Like, they've got loads and loads of threads. Those things are running. There's lots of concurrency. You don't really control what's going on. You know, if it's a modern program, it probably has an embedded JavaScript engine with a JIT compiler. Like, this is just dreadful. Let's not do that. All right, so really then, what we should try and think about is testing really, really old software, right? So then all I had to do was find a single node, single threaded distributed system written in 1985, like old enough that we don't have all these terrible practices. And I was able to find one, actually, incredibly enough. Here it is. Right. So you may be wondering now, how on earth is Super Mario Brothers a distributed system? I want you to hold that thought for 1 second. I will answer you. For now, let's just think about what it would look like to test this game really, really well. So the first thing you might do is you might write some like stupid unit test, right? So you've got your stupid unit test, like great, Mario can jump. That's good. But at some point, you need to test that the whole thing actually works, right? You need to test it like end to end, all the bits together interacting. And that's okay. We can write an end-to-end test as well. I should say, by the way, I feel almost dirty putting up a slide with Python code at this conference with like all these illustrious Zig luminaries. Maybe you guys can help me port this to Zig later. Okay, so you've got a Nintendo controller. Nintendo controller has 8 buttons. What that means is we can represent the state of that controller at any moment with a single byte, right? And the state of each bit in that byte represents whether you're currently pressing that button down. And then you can put together a bunch of these bytes. You can string them together into a big array. So for example, right, we've defined some powers of 2 here, and like, you know, this represents tapping the start button and then waiting for the game to load, because Nintendo's pretty slow. And then you run to the right a bit and jump and stuff. And the cool thing about Nintendo is that's it. This is all you can do to a Nintendo, is feed input into the controller. And so this array actually represents the entire state of the system, in some sense, right? And then we can take that array and we can feed it into a Nintendo emulator, and you get something that looks like this. So we tap the start button, wait for the game to load. Hey, right, okay. And we gonna get the guy? We got the guy, great. All right, so that's really cool. Let's reflect for a second on how good this test is, right? We are testing the graphics engine. We're testing the physics. We're testing the enemy AI. We're testing the controller input handling. And we're testing all these things together. This is a great test. There's only one problem with this test. The problem is people like us, right? The problem is developers, because developers are always changing their software. And this is very, very annoying. Because let's see what happens when we change this software. So I'm going to run the same input into my emulator again. On the left here, it's the exact same game. On the right, I've made a small change. See if you can spot it. All right, so I moved that block. See, I moved the block. All right, we still got the guy. Although that one didn't bounce on him. But it's okay. It's still a pretty good test, right? It's like, okay, we get it across the pipe. It's good. But now something bad has happened. Did you guys all see that? So what happened there? We made one teeny tiny change to this game. And suddenly our pre-recorded test input totally diverged. It's off testing a completely different part of the system. This game is highly chaotic. It's fragile. It's dynamic. It's like stateful. It depends on the entire history of its state at every moment. And Now, hopefully, this is starting to remind you of a distributed system, because distributed systems are exactly like this too, right? You make one tiny little change. Something gets a little bit faster or a little bit slower, or you change the order in which you do something, and suddenly it diverges, right? Its behavior actually looks very different. And this is what makes them so annoying to test. But what's so cool to me is that this is a big problem in testing distributed systems, but it's actually worse in Super Mario Brothers. Like, Super Mario Brothers is more fragile than your average distributed system. But it's also a lot simpler, and it's visual. It's easy to visualize, it's easy to think about and wrap your hands around. And what that suggests is maybe if we can solve this problem here and get good at testing Super Mario Brothers, maybe we can take some of the lessons we've learned and apply them in this much more abstract, much more difficult context. All right, so that's the experiment. See if we can do that. Before I do that, though, there's a couple other things that I don't like about this test, which I also want to run through. So one thing I don't like about this test is it's just taking one path through the game, right? We decided ahead of time what input we were going to run in there, and it's just following that one trajectory. And if you think about it, who's to say that that's where the bugs are? In fact, if you really think about it, it's probably not where the bugs are. Why? Because it's the input that you already thought of, right? You were able to write that test, so probably the bugs aren't there. Like, if you think about really bad bugs, the kinds that lead to production outages, like big, embarrassing debacles, they're almost always unknown unknowns. They're your system getting into some state that you had no idea it could get into, right? So what we want is something more like this, something that takes many, many paths through the game and tries doing all kinds of crazy stuff that you and I would never think of, that we would never write a test for, right? Like test jumping down into this pit on purpose, or getting up on this platform here and doing some wacky stuff. That would be way more useful, actually, if you think about it. Another thing I don't like about this is it's not taking advantage of one of our single biggest powers in the year 2023, which is that we have very, very cheap, very scalable compute. If I take that test I wrote in Python and I run it 10 million times on 10 million different computers, it's just going to do the same thing every time. It's not going to do any more testing or make my software any more correct. That's kind of a drag, because computers these days are very cheap and people are very expensive. And so if I can spend more computer time to save a bunch of developer time, that's like a really good exchange rate, right? Like that's like having dollars and exchanging it for rand. It's like really good. So I'd like to be able to do that. So how do people actually do this today? Well, in the computer game world, they get thousands and thousands of people to sit there and play the games for like weeks and weeks. And it's incredibly inefficient, incredibly expensive, and they don't even find all the bugs. And in the distributed systems world, like, let's admit it, we inflict it on our customers, right? And they find the bugs for us. It's great. Except it occasionally leads to really embarrassing outages. And there's one other problem. There's another thing about this that sucks, which is it makes it way more expensive to solve the bugs. And that's because of this fundamental relationship, which I think is not sufficiently well appreciated, right? So the cost of solving a bug increases in the time that that's been since the bug was introduced, right? Consider this point down here, right? You're typing your code, you're in VS Code or whatever, and you make a mistake. And maybe the IDE gives you a red squiggle, maybe your compiler spits out an error message, says you can't do that. That's really good, because you know exactly what the problem is. It's the thing that you just changed. You hit Control-Z, you're done. That bug costs nothing to fix. The exact same bug, if it's not caught early, if it's made, let's say, by your coworker 3 years ago, who then quits the company, right? And everybody else who worked on that part of the code has also quit the company, or they've moved to a different department in a different country. Nobody knows how it works anymore. And then you get like a bug report from production. And the bug report from your customer is something like, it didn't work, right? Like, that's now going to be a very, very expensive bug to fix. The exact same bug is like suddenly a million times harder. And so I think we're coming up with a list of what we want out of a good testing system for Super Mario Brothers. We want to walk backwards on this curve, right? We want to push it back this way. We want to find the bugs as fast as possible. We don't want to have that fragility problem that I showed you, where I move a single box and suddenly the whole thing breaks. And we want to be able to find the unknown unknowns. We want to be able to find the situations that we haven't thought of. And it's okay if in accomplishing these goals we use a lot of computer time, so long as we don't have to use a whole lot of human time. That sounds like a pretty tall order to get all those things, certainly for like arbitrary distributed systems. But Mario is a little bit easier, so maybe we can try and make this work for Mario, okay? Yeah? So here's a first naive idea, right? Just take totally random bytes and like stick them into the controller. All right, this is like the first idea. This has some good spots, right? It's definitely gonna find some unknown unknowns, right? This is gonna do things that no human being would think of doing to Mario. That's good. We wanted that. It's also going to use parallelism very effectively. If you run this on 10 million computers, it is going to do a lot of different things. And that's also good. There's just a big problem with this, which is that it completely doesn't work. And the reason it completely doesn't work, like if you draw a heat map of all the positions that you get to in Mario, when you just jam random bytes into the controller, you see there's a lot of stuff at the very start, and then it decays very fast, like it goes away really fast. Why is that? Well, it's obvious, right? It's like this guy. Like Mario has obstacles in it. There are these mushroom creatures that want to eat you, and there's like giant holes in the ground that you can fall into. The probability of getting past one of them with purely random exploration might not be too bad. Like let's say that the odds of getting past this guy is 1%, all right? 1% is fine. Like, well, I've got 10 million computers. What's 1%? Like a lot of them are going to get past the guy. But the problem is, in order to get real progress in Mario, in order to get anywhere, you don't need to get past one guy. You need to get past hundreds or thousands of guys. In order to beat Mario, you need to get past like all the guys. Now, you might be saying, hold on a second there, you just moved the goalposts, right? Who said anything about beating Mario? I thought the aim was to find bugs in Mario. So I'm happy to argue about this a bit in the Q&A section, but I basically think that actually in order to find all the bugs in Mario, or like a lot of the bugs in Mario, you kind of do need to be able to beat it. And the reason why is that in order to test any system effectively, you need to be able to explore its state space very effectively. And in order to do that, you kind of need to interact with it a little bit the way it was supposed to be interacted with. In the case of Mario, you kind of need to be able to play it, right? You need to be able to get up here and hit that thing and jump and do all the stuff that people do in Mario. And it can be hard to tell whether you're doing that really effectively. But I think if you can beat the game with your testing system, that would be a sign that you are doing it pretty effectively. So like I said, happy to argue about that more, but that is my claim. So here's the thing. Right? You ready? The thing that is so cool about this is this problem that you need to get lucky many times in a row, sequentially lucky, is the annoying part about testing Mario. But it's also the annoying part about testing distributed systems, right? Here is like the modal distributed systems bug, okay? And in order to make it happen, you need to first cause a leader election to occur, and then while that leader election is running, some transaction has to roll back. And then while that transaction is in some indeterminate state, something needs to go wrong, like there's a failure. This might seem like a contrived example to you. It does not seem like a contrived example to me. This looks to me like basically every distributed database bug I've ever seen. So what's so annoying about it? Well, let's say that you can make the leader election happen 1 in 1,000 times by just doing random stuff, like playing random operations against the database or randomly dropping packets or dropping connections or something. The problem is you don't just need that to happen. You need to make all 3 of these things happen, and you need to make them happen in the same run. And that means we're multiplying together their probabilities. So now, in order to find this bug, on average, it's going to take us 1 billion trials. That is a big enough number that your test system is never going to find this bug. But it's a small enough number that your users are totally going to find this bug. And this is what makes distributed systems like so brutal and terrible, in my opinion. So here's the cool thing though. Again, like this is an annoying problem with testing distributed systems, but it's even worse for Mario, right? To find a bug in a distributed database, you got to get lucky 2 or 3 or 4 times. To find a bug like on a high level in Mario, You need to get lucky hundreds and hundreds and hundreds of times. Like, forget 1 in a billion. The odds of doing that by randomness are like 1 over the number of protons in the universe or something. It's like, it's not gonna happen. So again, it seems like if we could solve this problem in Mario somehow, then testing distributed databases would be easy, right? That's the theory. So what can we do? Well, there's a third area of testing, which is neither Mario nor distributed databases, which has a really nifty trick that we can steal. And that area is fuzz testing, which Andrew also mentioned this morning. So for those of you who aren't familiar, a fuzzer is a program that feeds random inputs into some other program to try to get it to crash, basically. And usually the program that you're testing is like a thing that's parsing untrusted input from the internet and that's been written in C or some other memory unsafe language, and it's got buffer overflows, and it's really awful. And the Zig Software Foundation is going to totally solve this problem forever, but for now we have fuzzers. So if you think about it, a fuzzer also has to get sequentially lucky. It also has obstacles that it has to get past, right? The obstacles aren't mushroom guys and holes in the ground. The obstacles are things like checksums or validation subroutines, right? The fuzzer needs to somehow generate an input which is correct enough that it gets past all these obstacles, but also wrong enough that it can like trigger that off by 1 error in the software. And that also seems really, really unlikely. In fact, it is really unlikely. The key insight that the fuzzer people had, which I want to steal, is that this doesn't need to be totally random. Doesn't need to be unguided. We're allowed to observe the system as we're testing it and use that feedback to improve our guesses. In the case of a fuzzer, what you're usually collecting is coverage information, right? Like information about which branches have been taken or what code has run. And so the basic guess then is if you have some new input which finds some new code that you've never seen run before, right? And some new function you've never seen before. Well, maybe that's because it got farther through the parsing process. Maybe it's because your input was like more structured or more correct. And then you can take that same input and make a little tweak to it, like add a little bit on the end or change something in the middle, whatever. And that modified input is more likely to continue getting farther in the parsing process than if you started from scratch with a totally random input. That's the basic idea. And it turns out that this hugely helps. Well, how much does it help? Let's go back to our example, right? Suppose that instead of having to get lucky 3 times in a row, we could just get lucky once and notice that we'd made the leader election happen. Because some new code gets run or some log message we've never seen before gets emitted. And then we can say, great, I'm going to lock in that input and I'm going to keep it forever. And I'm only going to consider suffixes. And then I'm going to try and make this rollback happen. And then once I notice that, I'm going to lock in that input. And then I'm going to try and make the failover happen. Suddenly, the math is looking better, right? This is only going to take 3,000 trials now. It's a lot better than 1 billion. And in general, if you have n such intermediate points where you can notice that something important has happened and focus all of your testing energy from that point onwards, you get an nth root asymptotic speedup in the speed of this algorithm. That's not like a laughing, that's like really serious. Like you should take that if you can get it, right? So the thing is, there's only one problem with this example. Can anybody tell me what the problem with this example is? Why will this totally not work? It totally won't work. That's the next problem I'm going to get to. You're very advanced. Yes? Oh, you guys are really good. That's also not the problem, but I'm also going to talk about that. Yes! There we go. It's non-deterministic, right? So just taking the same input and running it again, you might have gotten lucky that first time you got to the leader election. It might never happen again with that input. And this totally explodes, blows up this whole idea. It means it's useless for testing distributed systems, unless you are a crazy person named Tiger Beetle, and you've written your database so that it can be deterministically simulated, which would be a very crazy thing to do. But I hear there are people in this room who've done that. Oh yeah, there's all these crazy people. Okay, but let's not think about this right now. Let's just go back to Mario and try to figure out if we can apply this idea in the case of Mario. So the thing about Mario, getting to, I think, your answer, is actually code coverage is a really bad measure of how deep you've gotten into Mario. The reason is you turn on the game of Mario, basically all the code runs. And then basically not a whole lot of new code is seen until you get to level 2. And it's just much too unlikely for you to beat level 1 with randomness alone. So we have to find something else. And it turns out in Mario, there actually is a really good guidepost to how far you are in the game. And that's the contents of memory address 0x86, which stores Mario's x coordinate. Because in Mario, how far to the right you are is a really good guideline to how far you are in the game. In general, I'm going to refer to this problem of picking something, some observable quantity of the system under test. Maybe it's code coverage, maybe it's log messages, maybe it's the value in memory somewhere. Picking such a thing that helps you bootstrap this process, I'm going to call that the problem of strategy. So Mario is simple, and so we can have a pretty simple strategy. Just go right as much as you can. So our new algorithm is take the current best input, as determined by how far to the right we are, and then add on some bytes. And take that and run it into the game and see if that number goes up. And if it does, it's our new best input. And if it's not, we throw it away and we try again. So who thinks that this is going to beat Mario? Wow, you're an optimist. Who thinks it's going to beat level 1? Most of you don't. That's because you're genre savvy. You know I'm only halfway through this talk. So there's no way it could work, right? Okay. So it doesn't work. And the reason it doesn't work is, I think, the thing you said, which is that we quickly run into a local minimum, or a local maximum in this case, right? So what's the problem here? The problem here is this is our best input. We're as far to the right as we can possibly get, but we are doomed. We're going to die. The thing about Mario is you don't have a lot of control over your fate once you're in the air. Your momentum either carries you through the jump or it doesn't. And there's nothing you can do about it. The crazy thing is, this also totally happens in distributed systems all the time. Why? Because in distributed systems, nothing happens instantaneously. All events take finite time. So let's suppose you're testing a distributed system and your strategy in that case is something like code coverage, right? So you're really, really deep in the query planner of your distributed database and you've gotten it to generate some crazy plan, which definitely has a bug in it. And your code coverage is through the roof. It's really good. But there's a message already baked in, already traveling from another node, which is going to clear the contents of that database. You're never going to find a bug in that case. It's just like this, right? No matter how many times we take this input and try to roll out from here, we're never going to find a bug. We're never going to progress in the game. So, and other examples of this in distributed systems, right? The node is about to restart, the test is about to end. Let's say you're testing something for trying to make it run out of memory. Maybe there's some operation which makes it allocate a huge amount of memory, but it's never going to allocate any memory again after that, right? That would be a dead end like this as well. So what can we do about this? Well, your first idea might be, I need to recognize somehow in my strategy that this state, I have no control authority, right? I should maybe only count states where I'm standing on the ground, where I do have control over my fate, and then maybe we can take that idea and somehow move it back into the distributed systems context and find some analogous thing. The problem is that also doesn't work because you run into this situation. So we've told it to get as far to the right as it can, and it has gotten as far to the right as it can. But what it was supposed to do is go through this pipe, because the real thing here is we've actually neglected a dimension. And I think this is a really cool image because of how clear it makes that. In general, all things equal, we want it to go as far to the right as it can. But all things aren't equal. It turns out in this case, going far to the right at different y coordinates has very different behavior, right? This is a higher dimensional problem than we've given it credence for. And that's pretty normal when you're testing real systems that aren't Super Mario. Usually there's not just one number you care about. So we need a better idea. So if there really is just one number you care about, you're trying to run the system out of memory, what you can do is just make your strategy a little bit less greedy. Instead of always storing the best input and always choosing that for further exploration, you can store a sample of inputs going backwards. And then you can choose from them with a probability distribution where you're usually choosing the best one, but you sometimes choose an earlier one. And that's good. What we're doing is making the strategy less greedy. And to be clear, that also makes it less efficient. This will get to the end of Mario slower, right, than the very simple one. But it's also less likely to get stuck in a dead end like this. And that's good. Another approach, which is a little bit more general, is to recognize the dimensionality of the problem. If what we're saying is, actually, your x and your y coordinate both kind of matter, well, maybe we should store both. Maybe instead of always picking the best x, we should consider all possible combinations of x and y and discretize that so there's not an infinite number of them. And then say, look, these are all sort of incomparable situations, and they're all interesting and unique, and we're just going to try and equalize our exploration across this grid. That's also less greedy. That also will beat Mario less quickly. But that's not entirely a bad thing. Because remember, our real goal here is not to beat Mario. Our real goal is to find bugs in Mario. Beating it is an instrumental objective. And the fact that this strategy is going to spend some time running into this wall or whatever, that's not so bad. Maybe there's a bug where you run into this wall, right? And I think when you've got something even less directional than Mario, like a real distributed database, it's more clear why this approach is good and why trading off a little bit of greediness is good. Okay, I've got another example with grids, but I'm going to skip it because I think you guys have got this idea. Let's go back to the real world now. So this is also not Zig. This is a really simple C++ program. This C++ program wants you to type, hello, my name is, and then something, and then please say hello, and then the thing you typed. So what's cool about this simple C++ program is fuzzers hate it. Conventional fuzzers have immense difficulty finding a bug in this program, which you can imagine I inserted here at this return statement. Imagine there's a seg fault right here. Why is it so hard? The reason, there's actually a bunch of reasons it's hard, but one reason it's really hard is this while true. So if we type something wrong, we don't exit the program. We just go around this loop again. What does that mean? It means that literally anything a fuzzer types into this program will increase code coverage. And your average fuzzer is very simple. It just wants one thing, which is to increase code coverage. And it's in luck. It's going to increase code coverage. Right? If it guesses something right, it increases code coverage on this branch. If it guesses something wrong, it increases code coverage on this branch and over here. And either way, you're just increasing code coverage. The problem is there's good and bad branches, right? There's ones that bring you closer to the bug, and there's ones that carry you farther away from the bug. But it's really hard to know statically which kind is which. And the same thing is totally true in distributed systems. It's just a little bit more subtle, which ones are good branches and which ones are bad branches. And I think this nicely illustrates why the problem of strategy is so hard, right? The strategy that a conventional fuzzer follows, which is to increase code coverage, is not sensitive enough. It considers as identical situations that are really, really different. Well, we could try something like consider all possible hypotheses of which branches are good and which ones are bad, and put them all in a big grid, right? Just like the grids we had in Mario. One of those hypotheses must be correct. We could score each of our inputs according to all of these hypotheses, and eventually the correct one has to make progress. It'll just be a bit slower. And the good news is that will totally crush this program. It finds the bug in this program, that approach. The bad news is it's completely unscalable. There's 2 to the n such hypotheses where n is the number of branches in your program, which is just completely unreasonable. And so you have an insufficiently sensitive strategy, and then you have a much, much, much too sensitive strategy, and we need to somehow find something in the middle, but it's really hard to see how we would do that. And in a distributed system, this problem actually gets even harder. Because then you don't just care about good branches and bad branches, you also care about the order in which the branch is executed and whether they execute on the same node or on different nodes. So it just gets worse and worse. Okay, I'm gonna actually skip my next slide as well. So let's suppose that I fixed all those problems and we now have a good strategy for beating Super Mario Brothers. Maybe we did this grid thing. Maybe we made like a less greedy version of our original thing. Who thinks it's gonna work now? You're an optimist. Yeah? All right. Let's see what happens. So I actually ran it. I ran that code for 45 minutes on a computer, and I got the best input according to our strategy. Here's what it looks like. And you see it's kind of bouncing, and it does get to the right. This is good. This is pretty good for a random number generator, right? But then it gets kind of stuck on this pipe, which is a little, okay, good, it got past the pipe, right? But then it gets stuck on this pipe. It's getting stuck for an awfully long time. This is not what we wanted, is it? What's happening? Why is this not working? We're running out of time. This is not good. Yeah. So that did not work. Can anybody guess what the problem is now?
It's not jumping high enough.
Yes, why?
Time isn't in the strategy.
No. That's a good guess, but it's not quite right. Yeah. Yeah, we're getting there.
To supply different inputs at the same time.
That not quite, but we're getting close. Yeah. Oh man, you win the free T-shirt. You give it to your friend. Okay, so the problem, this was going to be my hint slide, but he didn't need the hint. So the problem is, all right, we are feeding random numbers into the controller, and they're completely uncorrelated random numbers. That sounds really good, right? That should be the most random thing we could do. The problem is, in order to complete a jump in Mario, you need to be holding down the jump button for an extended period of time. Some of those jumps, it's kind of a long time, like 30, 60, 100 frames. The odds of any given frame having the jump button held down is 50%. Great, it's random. But the odds of having it held down for 100 frames in a row, that's 1 over 2 to the 100. You're going to be waiting a while. It totally doesn't work. So the really, really cool thing is this is also a huge problem in distributed systems testing. And it's not at all Mario specific. This is deeply tied into an important fact about the universe. And the important fact about the universe is that pure randomness, in the sense of white noise, in one sense, it's like the least predictable thing ever. But in another sense, it's the most predictable thing ever. Like consider this white noise, right? Say I take any window of it at any like scale or magnification and I can move it around, right? And I take my window and I average out all the pixels in that window. No matter where I go, it's always going to be about the same shade of gray, right? The standard deviation, always going to be the same. The kurtosis, always going to be 0. There's no higher order patterns. There's no periodicity. It's like the heat death of the universe. Maximum entropy at the micro level, but minimum entropy at the macro level, which is not actually what we want when we're testing. And it's very easy to make this mistake when testing distributed systems too. Let's imagine that you're testing a distributed database for network reliability, right? You want to make sure that it keeps working when there are network partitions. And the way you do that is you intercept all the packets, and then you flip a coin on each one, and if it's heads, you drop the packet, and if it's tails, you let it go through. That sounds really good, right? It's like the most random, right? But no, it's exactly the same problem as we just had with Mario. It's the most random from the point of view of each individual packet. But from the point of view of the system as a whole, it's actually not random at all. It's always going to look approximately the same. It's always going to look like just a slightly bad network. You're never going to get extended periods of total blackout and partition. You're never going to get extended periods when a whole lot of good stuff can happen. And that's not actually what we want when we're testing this system. So the good news is, and by the way, I should say, the general category of problems here, of picking a good input distribution for the testing problem at hand for you, I'm going to refer to that as the problem of tactics, okay? So the good news is that we actually do have some approaches that we can use to try and solve this problem too. Here's one that's easy to motivate in terms of Nintendo. Think about how a human being plays Nintendo. The way our random number generator played Nintendo is every frame, it makes an independent decision about which buttons it's going to be holding down. That's not how human beings play. The way a human being plays Nintendo is you're holding some buttons down, And then at some point, you might make a decision to start pressing a new button or to stop pressing a button you had been holding down. That suggests an algorithm a little bit more like this one. Instead of taking our random source and just feeding it into the controller, we remember the previous state of the controller. And then we use our random source to decide to start pressing or stop pressing a button, which here looks like deciding whether to flip a bit. It's like applying a mask with some low probability. Again, maybe this seems like, okay, cool, whatever, that's like some Nintendo thing, but it's like totally not. Like this weird trick will make all of your random distributions way more realistic and more lifelike, because again, it's like a truth of the world that pretty much all natural and man-made phenomena exhibit this statefulness. Like think about the weather for a second. Depending where you live, there's some probability that it's raining any given day, right? Let's call that probability P. So you might then naively assume that the probability that it's going to rain 2 days in a row is P squared. No, it's not. It's like much higher than P squared. The reason why is that if it's raining on Monday, it's then more likely to be raining on Tuesday than if it had not been raining on Monday. This is a true fact about how the weather works. Like you need to know this if you're building dams or reservoirs and stuff. Like this is real. And it's also true of network weather, right? The probability that there's a network partition happening at time t equals 1 is highly dependent on whether there's a network partition happening at time t equals 0. Why? Because new network partitions starting is a very, very rare event. I hope it's a rare event. Whereas a network partition that was already going, continuing for 1 more second, much less rare event. Users also act this way, right? Your users don't arrive randomly spaced out through time. You have no users, and then you suddenly have all the users, right? Like that's just the way the world works. And so this change is not just about Nintendo. This change will fix all of your testing problems. Not quite all of them, but it'll fix a lot of them. This is a cool paper which I do not have time to talk to you about. Ask me questions about this at lunch if you're curious. Okay, so we make that one little change to our random number distributions. We fix our tactics. Now let's see what happens. You ready? I've sped this up. You see it's jumping higher now, huh? It's jumping a lot higher. It's looking a little more natural, like a human. It's actually getting kind of far. Is it going to beat level 1? Who do you think is going to beat level 1? Yeah, it's going to beat level 1. All right, that's cool. It beat level 1, but level 2 is a lot harder. Is it going to beat level 2? I don't know, man. It finds the warp zone. There's the grid strategy at work. It actually warps straight to world 2. I'm not going to play this whole video for you because it lasts a really long time. Do you know why? Because it beats the game. But I will skip just ahead a little bit to Bowser's Castle, because in Bowser's Castle, something really neat happens. This is something I was not expecting. I didn't play a lot of Nintendo as a kid. My parents didn't let me have one. But in Bowser's Castle, there's a dungeon, and the dungeon is flooded. And in that dungeon, that flooded dungeon, we're going to get stuck. Okay, we're stuck right here. And then we just clip through the wall. Did you see that? Yeah, that was pretty cool. And so we just beat Mario. We found a bug along the way, and we rescued the princess. That's pretty cool, right? With a random number generator. Yeah. Okay. Now, are you guys ready for something really, really cool? Okay, so who here knows what a Kaizo Mario ROM hack is? All right, does one of you want to explain?
Too hard.
Yeah, right. Right, so Kaizo was this Japanese guy, I think, who basically made these modified versions of Super Mario Brothers, where he changed the rules of the game and like changed the levels around completely and made them way, way, way harder. So as an interesting experiment, I downloaded such a ROM hack, and I did not change the system that produced that movie that you saw at all. Like I swear, Scout's honor, I made 0 changes. And I ran it on the Kaizo Mario ROM hack. Let's see what it does. It like I'm not going to play this whole video because it totally crushes this too. And so this is now actually getting really exciting to me because this feels like it's sort of exactly the thing I said I wanted at the start of this talk, right? This is definitely finding unknown unknowns. I didn't know that you could clip through the wall in Mario. It's doing it pretty fast. Generating that movie that you saw, fully exploring the state space of Mario, took about 45 minutes on a single core. and it parallelizes really nicely. If you run on more machines, it'll run faster. It also isn't fragile. Like, forget moving a single block and my test input desyncing. This, like, I just changed the entire game, and I was still able to run it, and it's still able to like explore this game and find bugs in this game. That seems really cool. So now, like, how do we take this and apply it to distributed systems? Well, this is where we get back to that problem about determinism that I mentioned before. Because the trouble is, distributed systems are not deterministic. In fact, pretty much no software is deterministic, except for Tiger Beetle. So this is actually really bad, right? Because think back to my example here. It means we have to throw away this entire idea. It means it's just like not going to apply to our actual thing that we want to do. So my company, Antithesis, did something slightly crazy, which was, in order to solve this problem, we wrote a deterministic hypervisor, which can run any piece of software deterministically if it runs at all. If it runs at all, it will definitely run the exact same time given the same input, every single time. This is a really terrible slide, by the way, but I wasn't sure how to like visualize deterministic hypervisor. If you have some ideas, like, please tell me. But the basic idea here, right, is like we booted this VM twice. It's like an Ubuntu VM on two different computers, and we got the same hash of the memory at the end of the boot process. And if that doesn't seem really, really exciting to you, I mean, what can I tell you? It's actually really hard. So why should we care? So the reason we care is because what this does is it means you can take any piece of software and turn it into Super Mario Brothers, right? You can take any piece of software and turn it into a pure function from a stream of bytes to a guaranteed, uniquely determined state, which means now we can go take all those tricks that we discussed in testing Mario and apply them to all the other software in the world. So if you're a properly cynical engineer, that probably sounds like it's all totally fake. So you know, it's not fake. We have some real customers. Here are some of their logos. But actually, there's a big problem with this slide. The big problem is it's missing the most important one. Yes, right. So that's that. Feel free to ask questions.
Can I have a coupon code?
A what?
Have you not heard of a coupon code?
A coupon code?
So Will told me that he's happy to onboard you all as customers, and you just need to use the code SUPERCOOL, and then you
There you go.
into the program.
That's right. That's right. Send me an email with that in the subject line, and you're in. It's like cutting to the front of the nightclub.
Huge round of applause for you all. Thanks so much.